Hello, it's GWPS here. I'm going to go through some interesting curves today, and this is where you've got fractional polynomials. So things like x squared, and so on in the numerator and also in the denominator. Now, unlike standard graphs like quadratics and cubics and so on, we don't have a fixed shape that we can always rely on. And instead, what you've got to do is really break it down and consider what's going on at different parts of the curve. So we build up all these little clues and markers, and eventually we then draw our curve when we're ready. So what I propose to do is go through from scratch 3 base examples which will really illustrate the key ideas and help us understand what's going on. And then I'll outline a framework which we can use more generally to do more difficult looking curves. So let's get started with the most important example, which is y equals 1 over x, just the basic reciprocal sketch. And you may know what this looks like already, but I want to go through why it looks like that. Let's just start by drawing the axes. And for this curve, the thing you need to realize, and not just this one, but all of these curves, the most important idea I would say is that when you do 1 divided by a large number, you get a small number. And when you do 1 divided by a small number, you get a large number. That's really important. So consider 1 divided by 100, 1 divided by 1,000, 1 divided by 1,000,000. Those get very, very, very small. But if you do 1 divided by 0.1, 1 divided by 0.01, it gets very, very large. And so that's why with this curve, we get this very characteristic looking shape, like this. And then in the other side, it's negative, so it looks like this. The basic reciprocal shape. So with this, what happens is this curve gets closer and closer to the axis without ever touching the axis. And that's called an asymptote. And that's a very important idea. So we can keep going, and I could keep doing this. And the point is it never actually reaches this line. If you do 1 divided by a billion, 1 divided by a trillion, whatever it is, it's never quite 0. So we get very, very close. In fact, we get asymptotically close, but we never reach it. And that is what an asymptote does. Now, normally with asymptotes, we draw dotted lines to mark on where it is. But in this case, because it's the axis, both the axes, in fact, we can just leave it as it is because it's already there. And from this, I want to consider what happens when we have 1 over x minus 1. And the thing about this is, like before, if you consider what happens when x gets very large, you actually have 1 over a large number minus 1. And a large number minus 1 is still a very large number. So if this was 1,000,000, you'd still have 1 over almost 1,000,000. Even if it was 100, you still have 1 over 99, which is very small. So it doesn't actually change the behavior in the long run for large x. But when x gets close to 0 this time, it's different. So before, when x was 0, we went off and had an asymptote, but now when x is 0, this thing is instead just minus 1. You get 1 over minus 1. So we can actually mark on minus 1 here. We know it goes through there. But instead, consider, when does this denominator become small? And it becomes small when x is equal to 1. And so that's actually the key value. And this is what gives us the vertical asymptote. And so you can draw this graph, which will look like this. And on the other side, it in fact goes through this point here, the y-intercept, to look something like this. Okay, so this is a slightly different one, but it's following the same principles of large numbers versus small numbers. And one more example to show another key idea coming up. And now things get interesting, because when x is very large, you actually get a large number divided by another large number. And so what does that become? Well, let's have a look. Let's say x was 100. You get 100 over 99, which is a little bit more than 1. What happens when x is 1,000,000? You get 1,000,000 over just below 1,000,000, which is really, really close to 1. So actually, when x is very, very large here, you get y approaching 1 instead of 0. So instead of the curve ending up down here at the axis, it's going to end up at 1, which turns out to be a horizontal asymptote. So we mark that on with a dotted line. And we also need to consider what else is going on here. And a bit like before, when x is 1, or very close to 1, this becomes something divided by a very small number. And the x on the numerator doesn't change that. So we still get this vertical asymptote when x is 1. Okay, and a bit like before, and this is generally advice for all curve sketching, it's worth just working out what happens when x is 0. And in this case, when x is 0, you get 0. You get 0 over something, so that's 0. In this case, it's actually a root because it's where the graph crosses the x-axis. That's what a root is. And so now you can draw the graph because we know that it ends up going towards these asymptotes, and we know it goes through the origin, and it nicely does this. And so it's quite a nice little graph. Quite similar, you could say, to the ones before, but it's a bit harder to do this time because we need to consider the long-term behavior as x gets to infinity, and it's a little bit less straightforward. And the way we write this down, there are two ways really, you could say. I quite like to say for large x, what we have is y is approximately x over x, which is 1. That's how I would say it. The other way you could say is that as x tends to infinity, y tends to 1. So in this notation here, you've got this line, this arrow means tends to. So as x tends to infinity, y tends to 1. It doesn't mean x is infinity, it doesn't mean that y is 1, but it means you get asymptotically close. Whereas this way of writing it down is just saying y is when x is large, y is approximately x over x, which is 1. And basically when x is large, you can ignore this 1 because the x is more important. And that leads us on to this framework, which is, I think, helpful when drawing these graphs. And so the systematic process I would go through every time with these graphs is to consider the roots. And the roots really come from, as you can see in that other example, what's in the numerator. When the numerator of a fraction is 0, then the whole thing is 0. So consider the roots, and you can mark on the x-axis where it crosses. And then consider when is the denominator 0. And that gives you the vertical asymptotes, because when you do something divided by 0, you effectively get infinity. It's technically undefined, but you can think of it as infinity. So it sort of zooms off as a vertical asymptote. And then consider the large x behavior, is what I would call it, and that's what gives rise to horizontal asymptotes. So it might just be the x-axis, or it might be when y is 1 or y is minus 1, that sort of thing. Now, technically, I put an asterisk there because it doesn't have to be a horizontal asymptote. You can have oblique asymptotes, but don't worry too much right now. I'm not going to do that in this video. And then the other thing to do is consider any y-intercepts. So as usual, just let x equal 0 and think, does it cross the y-axis somewhere? And that's just useful to mark on. And when you've marked on all those things, then you can consider how to draw the graph. And usually the graph will be drawable from all the information you've got. But sometimes, and you'll see this in some examples, sometimes you have to go one step further and consider whether it's positive or negative. And you can split it up into regions or positive, negative regions, and that can help finish off the sketch. But the main bit is going through these key steps and having the systematic approach, and then it should all come together. So first example, and if you'd like to have a go at this yourself, you can, but don't worry, you can just follow along. And here we are. So with all these sorts of graphs, I quite like to just draw the axes first. It always feels nice just to have a set of axes to look at. And again, you don't need to use a ruler or anything like that. You can just draw them. It doesn't matter if they're a bit wonky, it's fine. And then so straight away we think numerator, when x is 1, this is 0. So that's our root. So we mark on here at 1. That is going to be the root. And don't forget, that's the only place the graph will ever cross the x-axis. That's important. And then you think, okay, let's look at the denominator. And when x is minus 2, this becomes 0, which gives a rise to a vertical asymptote. So let's mark on minus 2 and draw a dotted line like this. And then we think, okay, when x is really large, what does this become? And it really becomes x over x, which is basically 1. So we can mark on 1 here as our horizontal asymptote. And then we think, okay, that's pretty much it. What else do we need to do? Well, one more thing. What happens when x is 0 and you get minus 1 over 2, so minus a half. So let's just mark on minus a half here. And then at this stage, we're ready to draw the graph because we've already got our asymptotes and we know it goes through these 2 points. So you can kind of see that it's going to look like this. And so in this case, actually, because I've marked on these points, I would start by drawing it like that and then come through like that. And then over here, it's going the other way around. It's going to be like that. Now you might think, how do we know it wasn't, say, this shape? But the problem about this shape is, this would have to pass through the x-axis. So imagine it went like this to this. It would have to go through here at some point, and that would mean it had another root. But we know it only had one root, which was at here, at +1. And similarly, you might think, oh, but what if it did this instead? Well, again, we knew it had to pass through here and here. So that's why it was on this side. So anyway, I'll do another example and you can see further what's going on. Okay, here now we have 2x this time. So this is going to change things a little bit, but not too much. And do have a go yourself if you'd like. I think we've probably covered enough for you to do this, but if you want to watch, that's fine. Now, I'm almost forgetting what to do. Roots. Okay, so 2x minus 8, when does that equal 0? When x is 4. So mark on 4, probably somewhere about here. And then 2 minus x, when does that equal 0? When x is 2. So mark on 2 here. Now that's going to be a vertical asymptote, whereas at 4, this is a root. So it passes through at 4. Now, what happens when x is 0? That might be useful. You have minus 8 over 2, which is minus 4. So down here, passing through. And what else is there to say? When large x behavior. So let's just make a note. For large x, we have y is approximately 2x over minus x. We can ignore the minus 8, we can ignore the 2. They become irrelevant when x is really big. And when you've got this, we can just cancel the x's like you would normally. So this becomes minus 2. So in the long term, if you put a really large number in here, you'd get something very close to minus 2. So let's mark on minus 2. And this is a horizontal asymptote. And now we're almost ready to do this because we've got our lines, we've done our roots, and we've done our y-intercept. Everything's pretty much ready. And you know from this point here and this point here that you can see the shape of this graph coming out. It can't be down here because it has to go through this point 4. And so we can just go like that. And then similarly here, this is rather nice, we can go like that. And that's not a very good curve, but it's okay. It's understood what that is. It's just a sketch, and I'm sure you can do a better one. Can I use the same bit of paper? Yes, just. And so it looks a bit harder, but again, follow the same principles and draw the axis. And so what we got, when is x squared minus 9 equal to 0? And it's going to be plus or minus 3. And those are going to be our roots. So let's mark on roots. And then when x is 0, we're going to get this asymptote. So we don't mark that on because it is already there, the line. And so now we think about the large x behavior. And when x is really large, we end up getting y is approximately x squared over x squared, which is just 1. So we can mark on 1 here. So now we can think it's got to go through here and here. It's going to end up zooming up and down here. And it's got to end up along here as well. So you can start to see that it's going to be like this. And like that. And then draw that here. And then that's the sketch. Do note, by the way, that when you have x squared, when the function is only x squared involved, you get this symmetry. It's called an even function. And actually, once I put on an exam paper, I put this question on. I said, part of the graph y equals 1 over x squared has been drawn. And you had to complete the sketch. Almost everyone did that. And that's wrong in this case, because when x is negative, a negative squared is positive. So it's actually this. So do be careful about reciprocals. There can be some more subtlety to it sometimes. So moving on. If it's a bit more complicated, like here, I would, instead of just doing it straight off, before you do that, I think it's probably worth factorizing. Because here you've got common factor in the numerator. And so we can write x brackets 2 minus x. And then in the denominator, it's my favorite one, which is a, is that on the screen? Good, which is a difference of two squares. So we have x minus 1, x plus 1. And that just makes it a bit easier to read off the numbers. You don't want to be doing it all in your head. So we can now just draw our axes and then mark on the key points. So we've got 0 and 2 from the roots, 0 and 2. And now you've got 1 and minus 1, which are going to be the asymptotes. So, and then don't forget one more thing, large x behavior. What happens, we get y is approximately, now you might think it's going to be 2x minus x squared over x squared and ignore the 1. But actually we can go further. We can ignore the 2x as well. Because when you're looking at really large x, the higher the power of x, the more important it gets, the more significant the number. So x squared gets much, much bigger as x increases compared with x. X goes up linearly, whereas x squared goes up quadratically. So we're really interested in the highest order x terms. And in this case, it's going to be minus x squared over x squared, which is actually just minus 1. So you could put, a large number in here, and it might not be exactly minus 1, but the larger you put a number in, the closer to minus 1 it will get. So let's mark on that. Minus 1. Now we can think about what this looks like. You might think, is it going to be here or here? Well, it's got that 2, so that's good. We know it's going to be this one. And then we have this region here. And we know it's got to go through the origin. But while it goes through the origin, you've got to be careful, because we might think, oh, well, it's going to be this. But it could also be this. Or it could even be more like this. Or it might be more like this. So you do need to be a little bit careful here about pluses and minuses and whether the graph is positive or negative in these particular regions. So what I would do, well, rather what you could do is just substitute a number, and that's always a safe option. So if you just say, okay, let's look at half, that's between 0 and 1. And when you've got half, well, what's the denominator become? It's half squared, that's a quarter minus 1, that's negative. And the numerator, well, actually it's easier to look at this one, becomes half times something positive, that's positive. So we've got a positive over a negative, which is negative. So you can work out that this is a negative region between 0 and 1. And then you can do something similar for this region and put something like -half in, and you'll find out that this is a positive region. But what I would do instead is actually realize that with these sorts of factorizations like this, you can see that every time you go through a key value, like 2 or 1 or 0, a root or an asymptote, actually the graph flip-flops and it becomes negative if it was positive before, and it becomes positive if it was negative before. So when you go through one of these key points, you change sign or flip-flop. And basically here you were negative, here you were positive, negative, positive, and then it's negative. So that's actually quite a useful idea, that when you go through key values, the graph sort of flips sign. So it is a bit trickier, this one, but once you've got these positive and negative regions marked on, you then think, okay, well, it goes through this asymptote, well, reaches the asymptote, comes along here, and it goes through the origin, and now it's positive, and it zooms off to that asymptote. And then it becomes negative, because again, it flips, and that makes sense because it's now in this region, so you can draw it like that, and it still reaches this asymptote here at -1. Okay, and again, if you thought, well, what if it does this? Well, it can't do that, because if it did this instead, it would have to pass through the x-axis, giving another root. But we know that the only two roots are at the origin and 2. And to illustrate this point further about positive and negative regions, I will just go through a very slightly contrived question, you might say, where we can really use this principle. So here we go, and it looks very, very difficult. It looks very complicated. You've got a cubic in the numerator and in the denominator. But actually it's all factorized and nicely ready for us to draw. So if we just follow that principle about flipping signs between all the key regions, we can actually draw this quite quickly. So watch what happens. Or do it yourself if you like. Let's just mark on the key points. So 0, -1, and -2, those are our roots. So 0, -1, -2. And then 1, 2, and 3, those are our asymptotes. So it looks a bit peculiar. How's it going to have asymptotes here, here, and here with roots over there? It looks a bit counterintuitive. Let's just mark these on. Now let's just remember the horizontal asymptote. When x is very large, you get effectively x times x times x over also x times x times x. So we've actually got an asymptote at 1. And now let's just consider the sign changes. And the easiest way to do this is just go to the region furthest to the right. And in this region over here, all of these factors are positive. The whole thing's positive. So we're definitely positive over here. And then just consider that every time you pass through one of these key values, it goes negative or positive. So we're negative here, then we're positive, then we're negative, then we're positive, and then when you go through -1, you become negative, and then positive eventually, which is good because we know we end up at this asymptote, which is positive. And then you just draw it. So you go like that, and here it's just something like this. And we know that you don't pass through the axis because there's no root. We cannot come above the axis. All we know is we end up down here and down here. So somewhere in between it just sort of comes up a bit. And here we're positive. So again, that's the other way around. And then here we are negative. So you switch. But this time we are going through the origin. Here we're positive. So we're up here somewhere. And then we go through this -1 point. Again, it's a root. And then we're negative. And then we're positive. And so we end up somewhere over there. All I would say other than that is that if you want to practice more questions or curves like this, what you should do is go on to Desmos. Just do this on any browser. It works really quickly. And just write down a few graphs, just make them up and have a go at drawing it yourself. And then go on Desmos and sketch it, and it will tell you all the key points. Desmos is annoyingly good at doing this, but it is a really good tool. But otherwise, I hope this was helpful. Give it a like if you liked it. Otherwise, don't worry. See you next time. I'm a complete idiot. I blame the heat.